Hi, welcome to the statics tutorials. So we're still looking at two-dimensional particle equilibrium, but now we've got a problem that looks really different with the problem statement than some of the others that we've looked at. So in this case, we've got this mass here at D, which is connecting to a ring at A, so that's kind of similar. And then A is connected with a cable to the ceiling here at C, and then also to the ceiling here at B. What's different though is it says that the ropes can support a maximum tension of 2 kilonewtons. Find the largest value now for the mass at D which can be supported. It kind of looks like we don't have enough information to even be able to start on this problem, but let's just chug through it our usual way. So we'll do our free body diagram and then do our sum of forces and see what we get. So with our free body diagram here, we have the mass at D times 9.81 meters per second squared, so they have that mass in kilograms now converted over to a force in newtons. We have this connection FAC, which we've cut, so we're going to show the force in AC as FAC, and then we have some distance information on that. We have a horizontal distance of 9 meters and a vertical distance of 1 meter. So we'll draw our similar triangle on here and put in our 9 and 1, and then we'll do 9 squared plus 1 squared, take a square root. We get this 9.055. Do the same thing over here for FAB. Draw the force that's in that cable. Plug in our 10 meters as our horizontal distance. Our 1 meter here is our vertical distance. Take 10, square it, add 1 squared to that, take a square root. We get 10.05. Now let's take a look at sum of forces. We have our FAB component here. We have our magnitude times the 10 side, which is our horizontal side, divided by the hypotenuse, the 10.05. And it's going in the negative x direction, so it has that minus sign in front of it. Over here we have the magnitude of FAC times the 9 side of that similar triangle divided by the hypotenuse, 9.055. And it's going in the positive x-axis, so it has a positive sign in front of it. We can't really solve for it and get a number, but we can solve for it so that we have FAB as a function of FAC or FAC as a function of FAB. So for this one, I went ahead and just moved this FAB portion over to the other side of the equation and then just divided through by that coefficient. So I have FAB is equal to 0.9989 FAC. What we need to conclude from this is which one's bigger. So if we take a look at this, whatever FAC is, we're multiplying it by something that's less than 1. So FAB is always going to be less than FAC. Let's jot that down. Now let's go back to our initial condition that the ropes can support a maximum tension of 2 kilonewtons. So if FAC is the bigger one, then it's going to get maxed out first. It's going to be the first one to hit 2 kilonewtons, and then it can't go past 2 kilonewtons. So because FAC is bigger, we're going to go ahead and just plug this value in, and then that'll allow us now to solve for FAB. Let's take a look at the algebra in this step. So plugging in the 2 kilonewtons here for FAC gives us an FAB of 1.998 kilonewtons. Now let's do our sum of forces in the y direction. All right, in this equation, we have the magnitude of FAB, which was our 1.998 kilonewtons, times the 1 side, that's our vertical side of our similar triangle, divided by the hypotenuse, the 10.05, plus the magnitude of FAC, which was our 2 kilonewtons, times the 1 side divided by the hypotenuse, the 9.055, minus the MD times the 9.81 meters per second squared, because that force is acting down on point A here. So now we know everything in this equation except for MD. Let's go ahead and solve for MD. And the answer that we get is a little bit complicated now because we had a force that was in kilonewtons. When we divided through in that last step by 9.81 meters per second squared, then we wind up with a unit of kilonewtons per meter per second squared. So I need to go ahead and multiply this whole thing by 1,000, convert that back to newtons, then divide by the meters per second squared. That would convert it into kilograms. So it's going to be 42.78 kilograms would be the largest mass that we could support. And then let's go back and check the force in cable AD. And we can do that just by taking that mass and multiplying by 9.81. So let's see what we get. So from that calculation, we get a weight of about 420 newtons from multiplying the mass times 9.81. Checking that 420 is less than 2,000 newtons, so it's less than the 2 kilonewtons that we had here in the problem statement. Do be careful though with that final check. Some problems in some books and also some professors don't include this final cable that supports the mass as having this constraint. So if you have any questions on that, just make sure that you ask your TA or ask your professor, or look at the examples in the book. Some folks just only look at the forces in the two support cables up here. Thanks for watching.